Okay, good morning, everyone. Let's get started. So first of all, just reminder, our homework one has been released, so please start working on it as early as possible, because it does require you to implement. Good morning, everyone. Sorry. Let's get started. So first of all, just reminder, our homework one has been released, so please start working on it as early as possible, because it does require you to implement. Good morning, everyone. Sorry. Let's get started. So first of all, just reminder, our homework one has been released, so please start working on it as early as possible. Because okay. Oops. Sorry. Yeah, I accidentally kept the streaming. So the voice is kind of like um played out. Um pointer. Okay. So yeah, please start working on earlier, because as we emphasize a lot, it's nearly impossible that you can finish the programming section in just one day. Because even you are familiar, you feel like you understand well the whole algorithm procedure. When you implement and will test it on the real world data set, you always will see some kind of weird things to happen. Um, it's very likely because some subtle bugs or implementation errors. So please spend enough time for you to debug your program and make it runnable and get reasonable results on the data sets. Okay. And by the way, please start thinking about your course project selection, which we will be due, I think in the following week of next Friday. And then we'll request you to specify what kind of projects you want, and what's your team member if you're doing research project, right? And you should start go ahead to start, because we're gonna release the midterm project report soon. And typically it will be due like the week after the fall break, right? So yeah. Okay, so let us continue. So in the last lecture, when we discussed different variants of decision trees, and then we introduced a very important concept called overfitting. So overfitting, as it literally means, like you kind of fit the training data so well, right? This won't be a problem if your training data is perfect. There's no errors, there's no noise. That's fine. Overfitting is not a bad thing. However, in practice, data is not always perfect, right? Data is often filled with noises, corruption, errors, and so on. But if your model is still like that powerful, it can like perfectly fit the training data. There's a consequence, right? Because it can also well fit the noises or errors in data. Such kind of fitting kind of like mislead the training of your model and kind of deteriorate its performance in generalization capability, right? So we gave in the last lecture, we talked about, we use some like synthetic experiments to show how this overfitting appears, right? So, and then we show some like real world experiments, right? So this figure is picked up from Tom Michel's book, right? So we can see that the x-axis shows the number of nodes in the tree, meaning that when you keep growing your tree, you're making a model more and more complex. That means they can fit the data better and better. Remember, decision tree, in theory, if you don't limit its size and depth, it can perfectly fit whatever training data you give it, right? So, and y-axis shows accuracy. So I have two lines. One is the solid line, shows the error on training data, meaning that you use your decision tree to make prediction on training instances, say, and how this training accuracy varies. And this dashed line shows the test accuracy, right? So you can see that at very beginning, when you increase the size of tree, meaning you add more and more nodes, both the training and testing accuracy is growing, right? And then at some like turning point, you see that when you grow, when you continue to grow the tree, your test error won't improve anymore, and on the contrary, it starts to decrease, right? Meanwhile, for the training error, it is still increasing, meaning that okay, it's kind of like a fitting. It's kind of like fitting the data better and better, right? Because you're growing the tree, you can make the tree bigger and bigger, but it doesn't mean like your generalization performance is better and better. Instead, there's some turning point. After that, you kind of overfit the training data, and the consequences that your generalization performance is hurt, right? So this is from real data. That means like actually it's because of some errors and mistakes and noises in the training data, such that you overfit the training data. You kind of, on the contrary, deteriorate the generalization performance on the new data. Does it make sense? Okay, so since in practice, right, the errors in the training data, noise in the training data is inevitable. Of course, when we train a decision tree for practical applications, we don't want our tree to overfit the training data, right? So that means we need to restrict the size or the growth of the tree, right? So there are a variety of approaches to do this, right? So we're gonna go through them, right, one by one. First, the simplest approach is to just fix the depth of tree, right? It is very easy to modify your IP3 algorithm, right? You just count what is the level of the tree right now, right? If the level of that tree is bigger than some threshold, okay, I'm stop growing, no matter whether all my instances are unique label or not, right? I'm gonna stop and create a leaf node and perhaps using the majority label in the current subset as my label, right? And there's some kind of extreme case, meaning that I'm kind of extremely simplifying my tree growth, which is called decision stump. That is, I just grow the tree for one level. In other words, I just select one attribute to split the data set and grow the branches, and that's it, right? So this is called decision stump. Of course, decision stump is kind of oversimplistic. It's not overfitting data, it's actually underfitting data, right? But decision stump, as you see, will be very useful when we talk about ensemble learning, especially the bootstrap method, the ADA boosting method. The ADA boosting is a way to combine a set of like very simple and a very weak classifiers into a very strong classifier, and decision stump is one common choice to construct the weak classifier. Okay, we'll talk about that later. Okay, and the second approach is that okay, I want to find out some like measurement to reflect the generalization performance of my current tree. How can I do that? Instead of using the whole data set for training the decision tree or growing the decision tree, I'm gonna random pick up a subset of training examples. We use them as a held out set. So every time when we grow the tree, right? After we grow the tree, say I add a few branches and nodes, I'm gonna test my prediction accuracy on this held out set, right? If the held out sets, the accuracy on the held out set improves, meaning that, okay, looks like when I grow this tree in this way, it's gonna help improve the generalization performance. I kind of allow the tree to have these new branches and nodes, right? Otherwise, if the accuracy on the held out set decreases, meaning that this tree, this additional nodes and branches actually deteriorates the performance, the generalization performance. Now, then I just reject adding those nodes and branches in my tree and stop growing, and that's it. Right. So, to summarize, we're gonna split our data into two parts. One is the training set, one is held out set, right? And then we'll grow our tree on the training split and check the performance on the held out set after every new node is added. Right? If the growing tree hurts the validation set or held out set's performance, then we stop growing. Right? That's another common used strategy. And third strategy is called post pruning. So that is like, okay, let's try to grow the tree as deep as possible and as wide as possible, as large as possible until it stops growing. And then we use some kind of validation set to prune the tree. You can prune from top to bottom, from bottom to top. There are a variety of strategies. Or you can convert the tree into a set of roots. Remember, the tree essentially is a conjunction of roots, right? Each row is actually a path from the root to some leaf node, right? Then we can decide how to cut those roots. Right? This is called post pruning. The benefit of post pruning is that because you kind of like first grow the tree to be as large as possible. When you consider the pruning, actually consider how to prune the global tree structure rather than based on some like a substructure of the tree to prune. So there's some kind of conceptual advantage of doing this. Okay, so this is all about decision trees, right? To summarize, decision tree is a popular machine learning tool. It is very classical and is very widely used. It's very intuitive. Prediction is easy, and the essence of decision tree learning is a greedy heuristic approach, right? Remember, our goal is trying to find a small tree or a tree to be as small as possible. However, finding a globally minimum tree is NP hard. That's why you have to resort to a greedy heuristics approach. And a greedy heuristic approach essentially is just trying to, every time I'm just trying to find out the attribute given the current data subsets that can best improve the purity of the labels. Right? That's the idea, right? So if every time based on current results, I can best improve my purity, then I expect not after many steps, I can make my tree to stop growing in that every node will have unique labels. Right? And decision trees can be extended for regression as well. So we have discussed previously, right? You can just set a stopping criteria and then calculate the average of the labels. Remember, in the regression case, the label will be continuous, right? So you just take the average, right? And decision trees are also prone to overfitting because it's so powerful. If you don't restrict the growth of decision tree, it can overfit any classification data set you can get, right? So we need have to in practical usage. Also, we always need to specify some strategies to avoid growing the tree too much and to restrict the tree size. Okay, any questions so far about decision trees? No, it's not the most common. The most common will be just to restrict the depths. The first one. Yeah, because it's the easiest to implement. Yeah, because you don't need to like every time you just grow a node and test the validation performance, and it's pretty useful. It's pretty effective. But of course, if you want to do, if you have like a more kind of structure tuning in a more a finer granularity, maybe you can choose the second approach, or even choose the third approach. Yeah, but the first one obviously is the easiest one, the most convenient one. Yeah. Okay. Any other question? Perfect. So now we will we'll start to talk about okay. Before we proceed to the next concrete machine learning algorithm, we would like to step back a little bit to talk about some basic concepts and the fundamental insights in machine learning. Right. So, so we're gonna spend one lecture or two to give a brief introduction about computational learning theory. But don't worry, the theory is really light. We just want to reflect. We just want to reflect some important insights in this machine learning framework, rather than ask everybody to prove anything, right? So the math will be quite light weighted, won't exceed the scope of our homework 0. That's why you will see that why homework 0 is important, because the sample complexity bound we're going to discuss today or next lecture will rely on your understanding about the definition of random variables, independent variables, probability inequalities. Okay, so here's our plan. So we would like to explain a very important concept in machine learning. It's called empirical error and the generalization error, right? So you see that in practice, the empirical error is what you can get, but the generalization error is what you cannot get. So you always use some way to bound the generalization error or estimate the generalization error, but usually you won't get exact value of the generalization error. So we'll talk about that later, right? And we'll talk about our goal. The goal in computational learning theory is to invent mathematical tools or methodologies to bound or estimate the generalization error based on the empirical error. Okay. That's why if you're interested in computational learning theory, you will see all kinds of probability inequalities. So we're going to explain why. What's the rationality of introducing those probability inequalities. Then we'll introduce a fundamental concept in computational learning theory is called PAC learnability, probably approximate correctness learnability. It's a lengthy definition, but the intuition is straightforward. It tries to give you a sense what kind of learning algorithms can be viewed as efficient or effective for learning, right? So we're going to talk about, okay, in terms of data fitting, in terms of the generalization error, in terms of the probability. Right? And then based on those basic concepts, we're going to give a formal description about the principle of Occam's razor. So actually from the computational learning theories framework, we can use like simple mathematics to show why the principle of Occam's razor is good, and we should choose that. Okay, so let us just refresh our mind about the bigger picture of supervised learning framework, right? So we know that in the supervised learning framework, we need to consider the instance space, the label space, and the hypothesis, right? So hypothesis means that, okay, you have like a range of functions, and your learning algorithm aims to search over this range of functions to find one which kind of close to the ground truth labeling function, right? So we feed the labeled training data to our learning algorithm, and then the learning algorithm is search over the so-called hypothesis space to find the best one as the approximation to the ground truth function or target function, which give you the ground truth labels, right? And then once we have a new example, right, we can use our learned hypothesis to make prediction, right? That's whole framework for supervised learning. Any question? Everyone's comfortable, right? Okay. So we have discussed our first specific learner, which is called decision tree, right? And later we'll talk about perceptron, we'll call it least mean square, we will talk about ADA boosting, random forests and neural networks and so on. Right? So now, and also we have given the general idea or concept about overfitting, meaning that okay, you are fitting training data so well, but you generalize to new data badly, right? This is called overfitting. So this is so far what we have discussed, right? Okay, so now let us look at a more a bigger formal framework to describe those kind of things, right? So let us consider a machine learning model, right? It could be decision tree or could be any other machine learning model, right? So we have trained this model on some fixed training set, right? And then we deploy it in a while, meaning that we could test this model in all kinds of new instances in the instance space, right? And then the question is that how well will your learned model perform on future instances, on those instances you have never seen in your training data, right? So we're always interested to know that, right? And in other words, do we have like some like a theoretical tool or mathematical approach to estimate or quantify your learned model's performance in those wild examples? Okay. So to discuss this framework, right, to discuss this mathematical framework for estimating your generalization performance, right? So we're going to introduce several basic concepts, right? Okay, so first, again, we're going to talk about the instance space X, right? Namely, all kind of like instances could be used for training or testing. Right? And in many cases, this instance space is infinite, right? Because your features, your attributes could be continuous, right? And then we're going to introduce the concept called concept space, denoted by C. So concept space is defined as the family of the target functions you want to estimate or you want to learn from data. For example, the concept space could be polynomials. And if you want to learn concept space, meaning that you want to, from data, you want to learn some polynomial function as your ground truth labeling function. Or it could be like can be even larger, like all positive functions could be a concept space, right? So this could be like very large family of target functions, but you can define it freely. This is basically saying that, okay, if you want to learn a concept space, meaning that you're trying to restrict your learning task into a specific type, right? Suppose you want to learn polynomials, right? This is one type of learning task. You want to learn all positive labeling functions. This would be another task, right? We want to know, okay, under different types of learning tasks, what's the performance? What's the efficiency of your learning? Does it make sense? Right? Then hypothesis space H, right? So as we mentioned before, right, supervised learning essentially is a searching procedure, right? Given the labeled trained data, you want your data to guide you to search a hypothesis which you believe is closest to the ground truth labeling function or target function, right? Right. So if you're doing search, you always need to specify a search range, right? Hypothesis space is just a search range. What kind of candidate functions, set of candidate functions you believe is enough for you to conduct search. Then you search over the hypothesis space to find the best point, best member in this space, and you pick it up as your approximation to the ground truth. It could be different. A concept space could be very large. And in many cases, you might even do not know what is concept space, right? For example, I want to predict tomorrow's temperature, right? What's your concept space? You could say, okay, your concept space is trigonometric functions, but likely it's not that true. It's not true, right? Or you probably want to say, okay, your concept space will be periodic functions, right? Probably that's not true as well, right? But you can make it your concept space to be very, very large. Like I know that the weather, the temperature will definitely bigger than zero. I mean, the absolute zero in the universe, right? That's Kelvin temperature, right? And okay, no, I can define my concept space to be all the functions whose prediction is bigger than that absolute 0 degree, right? Well, that's reasonable, but that make your concept space super large, right? Right. So that's concept space actually defines or reflects some basic property of your target function. Yeah. But hypothesis space is actually chosen by your algorithm. Your learning algorithm needs to specify some range of function, and you want to search over that range of function, right? Sometimes your hypothesis space could be different from the concept space, could be very different. So that means like even over your hypothesis space, you find the best one, it's still far away from the ground truth. That is possible. That's definitely possible. Like, any other question? Later, we'll talk about even more about the difference between the concept space and hypothesis space, right? Okay, training instances, right? Training instances are essentially just labeled training examples, right? It consists of instances from instance spaces and their labels, right? So here, through our discussion about computational learning theory, we're mainly talking about binary classification. Just simplify our discussion, right? So you can view that each training instance is a pair of the instance from the instance space and the label from label space, right? And this label should be given by the ground truth or the target function, right? So what do we want, right? Once you have given this, right, you're given instance space, you're given concept space, hypothesis space, and the training instances. We want to conduct a searching procedure to find out a hypothesis in a hypothesis space such that our hypothesis prediction is exactly the same as the target function's prediction, right? This is the ideal case, right? This is actually the ideal case. The most ideal case will be, okay, for any instance in this instance space, my hypothesis will give exactly the same prediction as the ground truth. But we'll see that later. Right? This is like the most ideal case. In most cases, it won't be. You cannot arrive at a point, right? But at least, right, during the training, we want to find out a hypothesis such that the prediction in a hypothesis, the prediction made by our hypothesis on the training instances are consistent with the labels given by the ground truth, right? Ground truth function. Okay. So here, we're gonna introduce our important assumption, right? That is, we're assuming the training instances are generated by a fixed, unknown probability distribution over the instance space. Right? So this actually introduces some kind of randomness because the data is generated randomly, right? And imagine like all the images in this world, right? And underlying the distribution of these instances, right? Those images is a very complex probability density, right? But you don't know that. We know that, okay, each image is generated in some like random process or random procedure. But we actually do not know what's the distribution function on that, right? We even do not know whether there is some closed form to express the distribution density. But here, we assume that we only make a mild assumption that, okay, when we collect the training instances, we collect samples from this unknown complex distribution, right? It's like, okay, I want to train an image classifier, although I don't know what's the distribution of those images, right? They're too complicated. But as long as I pick up those images randomly, my collected images for training will still respect the unknown, though very complex distribution. Does it make sense? And then during the evaluation, we assume the wild new test instances are also joined according to this unknown data distribution D. Does it make sense? Right? It's like, okay, I have a classification task, right? I want a prediction task, right? I know over the instance space, there's a very complicated distribution over that. But you can pick up those instances generated by this distribution randomly and form a training data, right? And you train your model. And then if you want to test your model's performance, you just pick up instances generated by the same distribution again, then you test the performance. That's our basic setting. Any question? Yeah. Yeah. The distribution are known. The distribution of those features variables are known. Are unknown. Yeah, if you want to see in that way, yes. If you have an infinite number of the data sets, and the average of those values will converge the Gaussian distribution, that's for sure. Yeah, but for individual variables, there's no guarantee it's gonna be Gaussian. You can view like, okay, I have a very complicated distribution, right? And those distribution, all those instances are generated from this distribution. Like even you write a news article, right? You can imagine every news article are produced by some very complicated probabilistic machine, right? Because when you write down, you actually don't know what you're gonna write in the next word, right? You don't know when you're gonna delete some word and replace a different words, right? So this is a completely random process. Of course, it's not like a non-informative random process. You have some information there, but you have some uncertainty there, right? So you can view like, okay, all data in our real world are subject to some unknown distribution, but the distribution is super complicated, and you never wish you can find out some like a closed form to describe that distribution, right? Although there are some theories in that, okay, law of large numbers, right? You take the average of any random variables, and as long as the IID and goes to infinity, it converges to Gaussian, right? But when we talk about machine learning work, we're not dealing with infinite amount of data. Right? Another question? So we're talking about this setting, right? This setting, I'm saying this is like reasonable, because you're assuming, okay, you are gonna collect the training instances from this distribution, right? Meaning that you are not intentionally select or cherry pick those examples. And then you train a model, then you test your model on new instances or new examples drawing from the same distribution to see the performance, right? This is to make your evaluation of your learning algorithm to be more objective. That's the basic setting. But there could be any others. There could be other settings. Like I can assume, okay, the data distribution I use to collect the training instances can be different from the distribution I use to collect the test instances. That actually reflects some kind of like a, for example, I intentionally select the examples, I bias or distort the original data distributions by adding some additional selection procedure, right? Or other ways of doing that, right? So of course you can do that, right? But here we're going to talk about the most objective setting. Any question? Okay, yeah. Because understanding this setting is very important for us to understand a bunch of theory, because you see that when we talk about the sample complexity bound, the generalization error bound, they are all based on this assumption. That is, your test instances are joined in the same way as your training instances, right? And then you just say, okay, you just want to look at, okay, when your learning algorithms our learning model are trained on data sampled from this distribution, this complicated distribution, right? Where's your test performance on data from this data distribution? Does it make sense? Okay. So now let us first define what is the generalization error, right? So suppose your learning algorithm returns a hypothesis, of course, from some hypothesis space, right? I want to give a definition which quantifies its generalization performance. So this quantity is called generalization error, right? So the generalization error is defined as a probability that for any instance comes from this data distribution D, your prediction made by hypothesis is wrong. And that's it. It's just a probability you make a wrong prediction on any instance from your drawing from your data distribution D. Does it make sense? So this definition is pretty simple, but we want to be aware that this generalization error actually is dependent on the data distribution D, right? And unfortunately, this data distribution D, in most cases, is too complicated to know. We don't know that. It's easier for you to fetch instances from this data distribution D. Like, I don't know what's the complicated probabilistic machine that generates news articles, right? But it's very easy for me to pick up 1 or 2 news articles from the web. It's very easy, but we never know what is the distribution form for D, right? So just be aware of this. So to give a concrete illustration about the generalization error, right? So let us draw a big rectangle to represent the instance space X, right? So, and we use this circle to represent the instances which are labeled as positive by the target concept, meaning the ground truth, right? And suppose you have a hypothesis H, right? Your hypothesis H can also label all the instances in the instance space, right? So we draw another circle, or actually it's an ellipsis, right? To represent all the positive instances labeled by H, right? So you can see they're part of our overlap and part of non-overlap, right? So we could see that the error occurs in these non-overlapping parts, right? In those non-overlapping parts, this where F and H disagree. And the generalization error actually is the area of this non-overlapping part under the data distribution. Does it make sense? Right? Hopefully that's give you a concrete idea about what does the generalization error reflect. Any question? Okay, great. Okay. So because the generalization error depends on the ground truth, not ground truth, the data distribution, right? The data distribution actually is often too complicated to know what is the exact form on that. So that means calculation of this generalization error is often infeasible. You will never be able to know what is the exact value of the generalization error. So in practice, how can we quantify the error, right? So in practice, we usually calculate the so-called empirical error. So what's the definition of empirical error? It's very simple. It's just the training error. That's it, right? So this is kind of lengthy, but the basic idea is that, okay, when you have learned a hypothesis H, right, you use H to predict the label for every training instance. Then you just look at the error. That is called empirical error. And obviously, empirical error depends on the training set S, right? So that's why we denote it by error SH, right? The generalization error is dependent on the data distribution D, so we denote it as error DH. Okay, so now I want to test everyone's basic understanding about probability of random variables, right? So, okay. So is error D, H, a constant or random variable? Why is a random variable? Mhm. Yeah, but I'm talking about error D. D, the distribution is given. And H is given. H is hypothesis. Right now, we don't need to think about whether H has some randomness. Suppose H is given, right? It's a constant, right? So why is it constant? Because the data distribution is here. So you're actually calculating under this probability distribution, what is the chance that H of X is not equal to F of X, right? So if you want to write down this probability, you can write down as an integral, right? You can write down this integral over X over the whole instance space, and then you have a indicator function, right? And times this and integrate with this probability density of D, right? Right. That's the yeah. I'm saying like H is fixed. H is given. Yeah. So if we want to write it out, right? If you feel like it's help, I'm gonna write it out, right? So this is kind of like integration, right? X over the whole instance space that you have a indicator function, your H labeling X is different from your ground truth labeling, right? And then times P of D, that is the probability density on this data distribution on X, and integrate OX, right? That's the most precise or rigorous definition of the generalization error. You can see that there's no randomness here. Just integrating all possible probabilities, integrating over all possible instances, right? Each instance has probability density under this unknown data distribution, and you're going to take a look whether your prediction by H is correct, and then do this integration over the whole instance space, right? Does it make sense? Yeah, if you feel uncomfortable, just think about write down the definition like me. You'll get it, okay? So yeah, you have covered the key point. So the generalization error means that, okay, if you apply your learned hypothesis to in predicting every possible instance in the instance space, what is the overall error? Does it make sense? You like suppose your instance space contains like 1 million examples. The generalization error means that, okay, I want to predict my use my learn function to predict all of those every of these 1 million examples and see what is overall error. Same distribution. Yeah, we're talking about the distribution is fixed and it's consistent between training and testing scenarios. Right? Does it make sense? And here we emphasize that there's some distribution over the data, right? So it's not like, okay, every instance, every instance has same probability density, or they have varying densities, right? But here, to be general, right, we consider there's a distribution across the instance space. Then we're gonna look at under every instance in this instance space, whether I'm gonna make a correct prediction or not, right? And then do the weighted average under this probability density. That's the generalization error. Any other question? Everyone feels comfortable? Okay. So now the first insight is This guy is constant. It's not random variable because it has already, you can view it as an expectation, right? As an expectation. This guy is actually an expectation over the data density and of this fraction, this indicator function, right? This indicator function indicates whether you're doing correct prediction or not, right? And then the next question is, what about empirical error? Is empirical error a constant or random? And yeah, it depends on S. And then okay, so the empirical error depends on S, right? And S comes from, as remember, it's a training data set, right? So that means every instance in S actually comes from the data distribution, right? So that means S itself is a random variable. So that means error S, H itself is a random variable because it depends on the training set, right? And in this training set, in training set 1, you might get error 0.01. In next training set, you might get error 0.02. In third set, you get error 0.05, right? So actually it can vary along the training set. And then your training set is random variable. Of course, the training error will be a random variable as well. Does it make sense? Mm-hmm. Yeah. Yes. Yes, exactly. Yes. Yes. Very good. Very good. Very good explanation. Yeah, I'm going to emphasize again. I'm going to rephrase what he said again, right? To help you because this is really important. Otherwise, you'll get confused when we talk about, okay, what is generalization error bound? Why you can apply it in that way, right? So basically, the training error or empirical error is random because you can imagine in the training procedure, right? You're going to random draw a set of examples from the data distribution, right? So I mean, the training set itself is random. And in this time, you draw this part of examples in the instance space, right? Next time, you draw another part of examples in the whole instance space, right? So every time you have different set of data points to train. Of course, your training error will vary as well. So that's why your training error essentially is random. The randomness comes from the training data itself. Does it make sense? But the generalization error is actually computed based on the whole instance space, right? Remember the definition, right? The definition is that, okay, you're going to compute the error over every instance in this instance space. There's no like random sampling procedure. And then, of course, when you calculate this error, you're going to weight the error by the probability density and do this integration. So there's no randomness. You are going to use the whole instance space to calculate the error. That's why this is constant. Does it make sense? Right. So keep in mind, right? If you feel uncomfortable, just think about the definition of random variables and think about the definition of expectation and so on. Okay, so now we would like to formulate the theory of the prediction. So in our supervised learning framework, we have instance space, we have a unknown distribution over the instance space, that is the data distribution. And we have some unknown target function, which gives the ground truth label. This target function comes from the concept class C. And we have a hypothesis, comes from a hypothesis space. This hypothesis is learned by our machine learning model, right? And we have a set of training examples, which we denote as S, right? Let us assume we have M training examples in S, right? And the labels are given by the ground truth, the target function F, right? And then associated with a specific hypothesis H, we have empirical error, which measures how well H performs on the training set only. And we have a generalization error, which also called true error, which measures how H performs over every instance in the whole instance space, right? And again, I want to emphasize that the true error or the generalization error is constant, right? It won't change across different training set, right? But the empirical error or training error really depends on the training set, right? Okay, so given the settings, right? So here are a few critical theoretical questions which the computational learning theory aims to address. So first, as we mentioned, right, the generalization error is good. It kind of quantify your prediction performance across the entire instance space. You're not gonna miss any instance in the instance space, right? But you don't know the underlying probability distribution of the data. So actually, you'll never be able to compute exactly the true error, the generalization error, right? But empirical error, it is not very stable because it varies along the training set, right? It depends on which particular set of training data you're gonna draw from distribution. You're gonna train a model, right? But it's relatively straightforward to calculate, right? It's very easy to evaluate how your particular hypothesis H performs on this set of training examples, right? Then there's a question, right? Can we bound or can we estimate the real generalization error by our unstable empirical error? Right? That's one key question from the computational learning theory. And later we'll see how this can be achieved, right? The second thing is that suppose we are given a class of target functions, which we call concept class C, right? And can we assert that this type of target functions can be learned, or whether they are learnable? So here comes a question, right? What does it mean for learnable? Right? Which kind of like a behavior of your learning algorithm can we say, okay, this type of class target functions are learnable? Which type of functions are not learnable? Right? We should give a definition of learnable. Right? And the third question is more practical, like to learn a particular type of target functions. Right? How many examples does an algorithm need to guarantee some good performance? Say if I want my generalization error to be less than 0.05, how many training examples do I need? If you can answer this question, you can answer a lot of practical questions, right? So this kind of question is called sample complexity. Okay. And the last one is that what's the cost for an algorithm to learn a class C, right? That regards to computational complexity, right? Of course, you want your algorithm to be as cheap as possible. Okay. Okay, before we start to talk about the ideas to address those questions, right? We need to first make a realistic idea about how we expect our learning. Right? So first, we cannot expect a learner to learn a target function exactly. Why? Because you're learning from a finite set of data, right? You're not learning from an infinite set of data. In practice, you're always dealing with a finite set of training data. So you can imagine that there could be many, many functions, labeling functions exactly match your training data. Among those functions, there is only one ground truth. So it's not realistic to assume that, okay, you're gonna pick up the right one, right? From like say 10 or 100 functions, both are 100% recover the training data as labels, right? So there will generally be multiple functions consistent with the available data, right? And this available data as the training set drawn from the data distribution usually just represent a small fraction of available instance space. So you can't, you can't expect that, okay, based on this small representation of the instance space, you can locate the exact ground truth. Right? And second is more realistic in that, okay, because we're sampling, we're joining instances from the instance space according to some complicated data distribution, right? So remember, when you do sampling, it's always the case that you're going to draw samples from high density regions, right? The samples who have the high probability densities are more likely to be joined, right? In other words, like if your instance is rare according to the distribution, then it's less likely to show up your training data set. So that means like your algorithm, your training data will very likely to ignore those tail cases, right? Or these rare cases. Then it is likely that your learned model, your learned hypothesis will misclassify those uncommon examples. This is not irrational, right? It's actually it's pretty reasonable. Right. And the second thing is probably a little even more pessimistic in that we cannot always expect to, like, now that we cannot say, okay, our learner, our model can always find the target function exactly. But we can also now say we can always learn a close approximation to the target function. Why is that case? Right? Because learning also depends on the quality of the training set, right? So different training set will definitely lead to different learning procedure, right? If your training set kind of like well cover the whole instance space, then probably your learned hypothesis is a close approximation to the target function, right? But what if your training set is drawn to be only cover a small, a very unrepresentative part of the instance space? And then you cannot expect your learned hypothesis will be very good in approximation, right? So it really depends on the quality of your training set. And the training set essentially is random. It comes from some data distribution D. So that means like you also cannot say, okay, I cannot guarantee my algorithm will always exactly recover the ground truth, but I have a guarantee that it have 90% accuracy. It will always find out approximation such that its error is like less than 0.01. You cannot guarantee that because the quality of your learned hypothesis also depends on the quality of the training set, and the training set is random, right? It follows some distribution, and you cannot always guarantee your training set is high quality. Right? And then what is the realistic expectation? What is realistic what is a realistic expectation of our learning algorithm, right? What kind of like guarantees should we expect our learning algorithm can give? Right? That is, we make a probabilistic statement. Our realistic expectation of a good learner is that if with high probability, our learner will learn a close approximation to the target concept, then we will, okay, this is good. Why? Because this high probability consider the chances that I have a bad training data set, right? It means that, okay, no matter how you draw a data set, right? And my machine learning algorithm is good if I always have a high probability, like 0.95 chance to give you a hypothesis whose generalization error is less than say 0.1. So this is the realistic expectation, the realistic requirement for a good machine learning algorithm. Any questions so far? Okay. So now we have defined a criterion. We have defined a criterion, or we have defined our requirement or expectation of what a good machine learning algorithm will be, right? It means that, okay, given that the training data is random, given that your data set is finite, right? We hope a good learner has a high probability to return a close approximation to the target function. So that's our expectation, right? And now let us try to give a more specification about a good learning, right? So here we're going to introduce this concept called probability approximately correctness, or PAC learning, right? So PAC learning means that, okay, the standard or the criterion for a learning algorithm to efficiently learn some type of target functions. So here's the definition. It's a little bit lengthy, but quite the idea is quite intuitive. Right? So in PAC learning, one requires that we're given a small parameters epsilon delta. So epsilon indicates the level of the generalization error, and delta indicates the level of the probability. Then we say a learner is good if it has probability at least 1 minus delta. It produces a hypothesis with error most epsilon. It's a little bit formal, right? So we can get a concrete sense by substituting some specific numbers, like say if epsilon to be 0.05, delta to be 0.05. That means with probability at least 0.95. That's high probability, right? And the learner can produce a hypothesis whose generalization error is at most 0.05. So it's pretty good, right? So it's 95% of chance it will return your hypothesis whose generalization error is less than 0.5, 0.05. Right? Now, what kind of algorithm can be claimed to be PAC learn a type of target functions? Right? So here's the definition. Right? Consider a concept class C, namely a type of target function C, right? Defined over an instance space X, which contains the number of features N. And we say a learner L using a hypothesis H can probably approximately correctly learn concept class C if the following conditions hold. For every possible target function in C, and for every possible distribution D over the instance space, and for every possible error level epsilon and probability level delta, as long as you choose a number of training examples which is polynomial in 1 over epsilon, 1 over delta, feature number, and the size of hypothesis space H, then your algorithm guarantees to produce a hypothesis with probability at least 1 minus delta to make the generalization error at most epsilon. Then we say this type of target function C is probably approximately correctly learnable by your algorithm or learning algorithm L. Yeah, it's a little bit lengthy, right? So basically, okay, let me explain the key idea here. The key idea is that, okay, if we say L can efficiently learn this type of target functions, so pack-learn you can view like is efficient, right? It doesn't need too many training examples. It just need polynomial numbers to the requirement about the error level, the probability level, and the feature number and hypothesis space. It just need some number of examples polynomial in the scale of the problem. You can make you can have a high chance to find a hypothesis which has generalization error less than epsilon. So that's the key idea. So let's read this again, right? This is a little bit, again, this will be lengthy, right? But unfortunately, if you want to precisely express the idea, you have to use those notations and the lengthy definition, right? We define that the concept class C is pack learnable by L using hypothesis space H if for every possible concept target function in C, for all distribution D over X, and for any fixed epsilon delta, when the number training example M is polynomial in the requirement of the error level, requirement of the probability level, the instance space size, right? And the hypothesis space size, then the learning algorithm can have the high probability, meaning at least 1 minus delta, to find out a hypothesis in the hypothesis space that has error at most epsilon. Right. The number of features, the dimension of feature vector. Yeah. So yeah, to be more precise, it should be dimension of feature vector. Like for example, if you have a real feature value for each feature, right? Then your instance space should be R over N, right? R to the power N, right? So N is just the dimension of feature vectors. Right? So I want to emphasize again, right? Pack learnable means the efficiency in terms of the sample complexity, number of samples required to achieve some certain learning performance. Right? This certain learning performance is described in terms of the error level and the probability level, the dimension of feature vectors, and the size of hypothesis space. If to achieve a performance that is the L has at least 1 minus delta probability to find hypothesis with error at most epsilon, the required training examples is just a polynomial in this 1 over epsilon, 1 over delta, N, and the size hypothesis H. Then we say this algorithm can learn this type of target functions in a pack way, meaning probabilistic approximate correctly. In other words, if your required number of training examples, M, is growing faster than polynomial, like say it growing exponentially, or even more than that, then this concept plus C is not pack learnable. Meaning that it will be very hard for this algorithm to learn that. Why? Because you have to collect so many training examples, right? When you increase the requirement of the will increase the requirement of the error and the probability. Does it make sense? Any question? And if you still feel a little bit uncomfortable about this lengthy definition, I totally understand. Just read through these concepts for 5 times, you get. But here the key is that we want, if we say, okay, an algorithm, a model, a machine learning model can pack learn some type of target functions, we're saying that, okay, we do not need too many training examples to get a certain level of generalization error with certain level of probability. And that's it. And then the remaining the details of definition is just talk about what do you mean by do not use too many examples. It means just polynomial in those requirement about the error, about the probability, about the feature dimension, and about the hypothesis space size. Mm-hmm. No, in most cases you don't know that. This is just the definition. This is the definition. This definition tells you, okay, it give you a bar, right? It give you a bar, tell you, okay, which kind of algorithm is real kind of efficient, learn some type of target functions. The PAC-learn gives you the criteria. And as to whether in practice, whether you can show a particular algorithms is really PAC-learn some kind of concepts, that's another story, right? You have to show this, right? There could be a lot of tricks. And even with a lot of tricks, you cannot show that. It's possible. Another question? Okay. So, yeah, we want to emphasize again, the epsilon here indicates the generalization error you require your algorithm to achieve. And delta indicates the confidence level, right? So we want our algorithm to be like with high confidence, meaning with larger probability to find the hypothesis with as small generalization error as possible, right? And PAC learnability just indicates, okay, when you decrease epsilon, meaning that you want your learned hypothesis to be more and more accurate, and with the increase of confidence level, that means you want your learner to have more and more higher probability to find this low error hypothesis. The required training examples is just growing polynomially, not exponentially. Then you could see, okay, your learning algorithms is good, right? It can PAC learn this type of target functions. Again, if you feel uncomfortable after class, please read through this definition for 5 times or 10 times. You'll get it. Okay. And we can further define that the concept class C, or the type of target function C, is efficiently learnable if L not only just require a polynomial skill to this requirement in terms of number of training examples, but also the search over the hypothesis space or the finding of the hypothesis in time is also polynomial in those problem requirements. So it basically means that, okay, if you say L is efficiently, C is efficiently learnable, PAC learnable by L, if L not only just need a polynomial number of training examples M, but also the time complexity is polynomial to those 4 numbers. There's both lower sample requirement, lower sample complexity, and the lower computational complexity. Okay. So to summarize what is PAC learnability, we impose 2 requirements. First, polynomial sample complexity. Right? This is kind of like information theoretic constraint, meaning that, okay, if we want to increase the generalization accuracy, in other words, we want to decrease the generalization error, we want to improve the chance to get low generalization error hypothesis, we don't need our training examples to grow too fast. We just need a growth to be polynomial. That means that, okay, our learner can effectively leverage the sample information to find the hypothesis, right? You don't need like a explosion of number of training examples to help you to find a good approximation. You just need a mild growth of training examples to find a better hypothesis, right? And also polynomial time complexity. This is regarding to the computational complexity, right? So your algorithm, the search and procedure itself should be computationally efficient, right? So another insight about PAC learnability is that for every possible concept class concept or target function f in C, there must be a hypothesis in a hypothesis space such that your f, the difference between your h and f can be arbitrarily small, right? Remember, this is the definition of partial learnability, right? We want that for every possible f and for every distribution d, right? And for every possible epsilon, right? Your epsilon can be arbitrarily small. Of course, it's bigger than 0, but it can be arbitrarily small, right? And then you can always have a high chance to find out a hypothesis whose true error is at most epsilon. That means, okay, you can roughly view like for any target function, you can find out a hypothesis in a hypothesis space which is actually close to f, right? So there's a reasonable assumption that okay, you can assume that okay, your hypothesis space is large enough, it contains C. Right? If your hypothesis space is the same as the concept class, then we say it's a properly packed learnable. Right? So this is the definition. So okay. So from the definition of the packed learnability, we see this is a kind of description under the worst case. Right? It requires the algorithm must meet its accuracy for every distribution, right? That is a distribution-free assumption, right? And for every target function f in the class C, right? So it's kind of like in the worst case, you should be able to achieve that. Right? So that's the definition of packed learnability. And someone may ask, okay, do we have additional alternative definition about other types of learnability? Yes, of course. Right? And here we just introduce the most common used one and most fundamental one. Okay, hopefully everyone will feel comfortable to understand this definition. This is really important for us to get some insight about machine learning framework. So please spend some time to review our slides and look at those definitions and make sure you feel comfortable about those definitions. Okay, see you on Thursday.
About multiple learning or